That question you just asked, an AI took about 10 times more electricity than a Google search. That does not sound like much, but multiply it by billions of queries a day, add the months of training that taught the model to answer in the first place, and the numbers become staggering. In 2024, data centers worldwide consumed around 415 terawatt hours of electricity. That is roughly 1.5% of all the electricity generated on Earth. By 2030, that number is projected to double to nearly 1,000 terawatt hours. To put that in perspective, 1,000 terawatt hours is more electricity than Japan uses in an entire year. It is more than Germany, France, and the United Kingdom combined. And the single biggest driver of that growth is artificial intelligence. Today, I am going to break down exactly where all this power goes, why AI is fundamentally different from anything the grid has handled before, and the emergency solutions the industry is building to keep the lights on. A data center consumes electricity in three main categories: IT equipment, meaning the servers, storage, and networking gear, accounts for roughly 40 to 50% of total facility power. This is the productive load, the electricity that actually does the computing. Cooling systems, the chillers, fans, pumps, and cooling towers that remove all the heat generated by that equipment consume another 30 to 40%. Everything else, lighting, security systems, UPS losses, power distribution losses, and on site offices, takes the remaining 10 to 20%. The ratio between total facility power and the power actually reaching the IT equipment is called PUE, power usage effectiveness. A PUE of 1.0 would mean perfect efficiency, every watt goes to computing. The global average is around 1.55, meaning for every watt of computing, the facility uses an additional 0.55 watts just to keep everything running. The best hyperscale facilities achieve PUEs of 1.1 to 1.2. Some older enterprise data centers still run above 2.0, meaning they waste more electricity on cooling and overhead than they use for actual computing. This is the baseline. Now let me show you what AI did to it. A traditional enterprise server rack running web applications, databases, and business software draws 5 to 15 kilowatts of power. A rack packed with AI training GPUs draws 60 to 100 kilowatts. Some next generation configurations are pushing toward 150 kilowatts per rack. That is a 10 to 20 times increase in power density in under a decade. Nothing in the history of electricity infrastructure has scaled this fast. But it is not just the density per rack, it is the sheer volume of racks being deployed. In 2025, the five largest technology companies spent over $400 billion on data center infrastructure. That is more than double what the entire US electric utility industry invested in generation, transmission, and distribution combined. Let me say that differently. Five companies are now outspending the entire American power grid on energy adjacent infrastructure. And the projects are enormous. Meta's Hyperion campus in Louisiana covers 3,650 acres. That is twice the size of the state's international airport and 4 times the size of New York's Central Park. At peak capacity, this single facility would consume roughly half the electricity of New York City. OpenAI's Stargate project envisions multi-gigawatt data center complexes. For context, 1 gigawatt is roughly the output of a nuclear power station. Here is where the story gets serious. For the past 20 years, electricity consumption in the United States was essentially flat. Efficiency gains in appliances, lighting, and industry offset population growth. The grid was stable. Planners could forecast demand years in advance. AI broke that stability overnight. US data center electricity consumption is projected to rise from about 4.4% of total national consumption in 2023 to between 7 and 12% by 2028. In absolute numbers, that is a jump from 176 terawatt hours to as much as 580 terawatt hours in 5 years. The problem is not just the total demand, it is the speed. Building a new power plant takes 5 to 10 years. Permitting and constructing high voltage transmission lines can take over a decade. AI companies need gigawatts of new capacity in 2 to 3 years, and the concentration makes it worse. Data centers do not spread evenly across the grid. They cluster in specific locations: Northern Virginia, Texas, the Pacific Northwest, Ireland, the Netherlands, and they hit the local grid like a freight train. In Virginia, data centers already account for nearly 40% of the entire state's electricity consumption. The utility, Dominion Energy, is planning 27 gigawatts of new generation capacity by 2039 just to keep up. In March 2025, Virginia narrowly avoided power cuts when 60 data centers simultaneously disconnected from the grid during a disturbance. That is not a hypothetical risk, that is a real event that happened. There are 5 approaches being deployed simultaneously, and none of them alone is enough. 1. Efficiency. Every generation of AI chips gets more efficient per computation. Token costs have dropped 280-fold in 2 years. Power per AI query is falling rapidly, but total demand is growing faster than efficiency is improving because the number of users and the complexity of tasks keep increasing. 2. Renewables. Tech companies accounted for roughly 40% of all corporate renewable energy purchase agreements signed in 2025. Solar, wind, and battery storage are being built at massive scale specifically to power data centers. 3. Nuclear. This is the big bet. The pipeline of agreements between data center operators and small modular nuclear reactor projects has grown from 25 gigawatts in 2024 to 45 gigawatts today. Microsoft, Google, Amazon, and Meta have all signed nuclear power agreements. Nuclear provides the one thing renewables cannot: constant baseload power that runs 24 hours a day regardless of weather. 4. On-site gas generation. Constrained by slow grid connections, many operators are building their own natural gas power plants directly on the data center campus. Meta's Louisiana facility includes a 2 gigawatt gas plant. This solves the speed problem but creates emissions challenges. 5. Grid modernization. Governments are beginning to fast-track permitting for transmission infrastructure. The US, UK, and EU have all signaled policy changes to accelerate grid investment specifically to support data center growth. Here is what makes this moment different from every other energy transition in history. The electrification of cities took decades. The adoption of electric vehicles is happening over a generation. The growth of industrial electricity demand was gradual and predictable. AI data center demand is exponential, concentrated, and arrived faster than any grid in the world was designed to handle. The technology companies building these facilities have more capital than most governments. They are now the largest single driver of new electricity demand on Earth. And the infrastructure they need, the power plants, the transmission lines, the cooling water, the physical buildings, cannot be conjured with software. It has to be designed, permitted, and built in the physical world. That is the tension at the center of the AI revolution. The most advanced digital technology in human history depends entirely on the oldest industrial challenge there is: generating enough electricity and moving it to where it is needed. And right now, the physical world is struggling to keep up. That is the story, not the AI in your pocket, the power behind it.